Welcome, everybody, to the SEG Near Surface Geophysics Technical Section Hydrogeophysics Subcommittee's webinar. Our speaker today is Jeff Pettifer. He has worked for 25 years in the federal, state, and international geological surveys, and he has more than 27 years in geophysical consulting services at GHD and also at SMEC. He is principal of his own small company, Terra Ethos Geoscience Pty Limited, and Earth Science Enthusiasts. So without any further delay, let's turn it over to Jeff for an interesting presentation.
Yeah, hopefully it's interesting. Thank you, Laurie. Yes, I can't believe that I'm being paid to do what I love to do in terms of my science. And I'm 76 this year and still young in mind. And the projects are just getting better and better, and our science is getting better and better. So I'm hoping that this talk will encourage you to perhaps consider not a research career, but maybe come out into the private sector, where a lot of bright young people are needed to tackle the world's problems, and they're just growing and growing and growing. Unfortunately, a lot of the geoscientists are now seeing the value of geophysics, so that's a good thing. The first point I want to make, though, is the nobility of our profession. We are a noble profession, and nothing more noble than if I refer you to the leading edge article on mapping the geophysics to the Sustainable Development Goals. And when you go and read this article, which I encourage you to do, you'll find that a lot of the near surface geophysics maps into these goals really, really well. Perhaps the most noblest thing you could do is clean up all this unexploded ordnance, and unfortunately that crazy people have left lying around the world with all their conflicts. But also just things like sustainable mining and sustainable of the environment. Entheos is a Greek word for enthusiasm. In the old days, people that were enthusiastic were said to be possessed by the gods. Well, I'm certainly possessed by the geophysics gods, and so much so that I formed my own company, Terra Entheos, which I use to consult with my current company, SMEC. And yeah, I encourage you to be enthusiastic and be a nerd. It's just be unashamed about it. Now, the important thing for me is my touchstone. When I was a third-year high school student, I received a book prize called The Boy's Book of the Earth Beneath Us, and I just fell in love with geophysics and all the things about, those days it was mostly about solid earth geophysics, and all the things that you could learn about the earth. And whenever I get down and I have a bad client day or a bad data day, I just get that little book out and go back and read it and just reinvigorate myself and understand why I'm here doing what I do. The other thing that I read was a book, a very interesting book, My Experiments with Volcanoes, who was it was written by Thomas Jagger, who was the founder of the Hawaiian Volcano Observatory, and I managed to go to an SEG conference a few years ago. Laurie was there, and I managed to get a picture of myself with the great man who's also one of the people that's inspired me to get into geophysics. But one of the things he said was that they used to go out and measure the lava pools in these volcanoes on a daily basis, and they had years and years of data. And of course, they didn't have computers to do Fourier analysis, so they had to do it all by hand, calculator, and they broke it down into their components and found that there was this correlation between the sunspot cycle and the tidal levels in these lava pools. Now, as a young high school student, I was just absolutely fascinated. How could the sun influence the tidal influence in a volcano? So I just wanted to learn more about what geophysics was about. Another important thing is right from the word go, I encourage you to join a society and give back. The society landscape's a bit complex in the US. It's a bit simpler in Europe, but please encourage you to join the society that you're most comfortable with and learn from others and then also participate and volunteer progressively and give back. So the key thing to know, one of the key things to know, it's about the geology, stupid. And it really is about the geology, but it's also about our clients, and it's also about the applications that they want to know. Now, the clients don't always understand the geology, and they also perhaps don't understand what their problem is and what is the best solution. So often we're faced with prescriptive tenders or prescriptive job descriptions. So you have to be across the geology and as you get more experience, be more assertive in explaining to the client exactly what you think the problem is and what you think might best work for them. And of course, you're always restrained by budget and also the client's preconceptions. Because people are just being people, and the important thing is that there's so many aspects to our work. You're working with clients all the time who may or may not understand geophysics. You're working with colleagues that are maybe hostile to geophysics, other geoscientists that may be very amenable to geophysics, engineers, geologists, geochemists, and environmental scientists. But the most wonderful thing is just getting out there in the field with people that are keen to learn. This is a project that I was lucky enough to do early in the 2000s. I had about 5 projects in China with technology transfer. In this case, we were bringing a logging equipment and a resistivity equipment to Liuzhou, where they make the Qingdao beer, which you probably all had a drink of at some stage. And but they have a massive seawater intrusion problem there, and so we brought them some equipment, did some training with logging equipment and resistivity equipment to tackle that seawater intrusion problem. Frenemies, it's important to know that your friend one day can be your enemy in terms of competition within the consulting sector. So it's important not to make enemies. It's important just to keep good relationships. Never badmouth your opposition. Always just try and show how you think the services you offer are better, but never put the others down, because you may be working in competition on one day and you may be partnering with them to get a much bigger job with your combined forces next day. So yes, keep your friends and close. And when I say you're working with people that may have different characterizations, different training from you about a site. And of course, there's this famous blind men and an elephant saga about all these different people who were blind and bound by their preconceptions. And when they sort of touched this elephant, they all thought it was different. So geochemists and hydrogeologists and environmental scientists and just ordinary geologists and engineers, when they look at a site, they all think of it differently. And we as geophysicists have to be aware of this. And basically, if we're going to be a good geophysicist, meet these people more than halfway in terms of their conceptions and try and educate them in what we think is going on. The other thing, and perhaps another way to do this, is think of geophysics as geochemistry, because most of what we measure, most of the properties we measure are related to the chemistry of the rocks, whether it's reflectance from remote sensing, whether it's radioactivity of the surface soils in radiometrics, whether it's magnetic susceptibility for magnetics, which is magnetite geochemistry, and whether it's just the bulk density or the bulk properties such as density or seismic velocity. So that's one way of bridging, at least with the geochemists and the geologists, with our science. The other important thing I want to emphasize is variety. if you're going to start out as a geophysicist, I would recommend that you don't do 5 years of the one method. You try and encourage your boss to give you 1 year's experience in each method, so that after about 5 or 6 or 7 years, you've basically got most of the geophysical methods that a good near-surface geophysicist has in their toolbox. And I'm talking about just P-wave velocity, S-wave velocity, resistivity, electromagnetics, gravity, magnetics, geophysical logging. And then I'm lucky enough to have, in my 57 years, to have pretty well covered just about every method there is, basically airborne, ground, marine, downhole, for at least 2 or 3 years of each of those methods. So, and that just opens up the possibilities for a very rich career if you have that variety. You can have 7 years experience, but if it's all of the one experience, and you're all a seismic person, then seismic your hammer, and every problem seems to be a nail, when in fact it's much more complex than that. So one of the things that I encourage you to do particularly is to get involved in geophysical logging, because that is the most accurate, and getting down at the rock scale, getting into those rocks and down at the rock scale where you can actually calibrate your geophysical measurements very, very closely to the petrophysical properties. And logging is a very important tool that I encourage everybody to get involved with, not only in just running the logs, but also in doing the petrophysical analysis. And when you have this variety, it's amazing the sort of opportunities that open up to you. This is another job we did in China on the Yangtze Delta, where we were working 25 kilometers from a city called Dongtai, right on the coast we were. 400 years ago, Dongtai was on the coast, so that's how much the silt has built up on the Yangtze Delta, and 25 kilometers of so forth, and they were reclaiming the land. Every 3 years, they would go out into the tidal flats, build a seawall, and reclaim that land. And of course, they would then have to drain it and get the salt out of the soil and so forth. So they needed an EM system to map it. So we came up with this monstrous, with an EM31 on the front and an EM38 on the back in that little barrel. And we could orient the EM38 horizontally or vertically and so forth. And then we built this back in Australia, and then brought it over there and put it on this tractor. And I'm not sure if it's still operating today. The other thing I want to say is, from little things, big things grow. It's a very popular folk song in Australia. But it's true. From very, very small jobs, you never know where it might lead you. For example, we did a $20,000 gravity survey for a client in Bangladesh. The next job, they were so happy with that work, the next job they gave us was $500,000, and they said, don't worry about the money, just keep invoicing us month to month. So the next thing I know, I was living in Bangladesh for five months of the year, and got to have work with some wonderful people, and we did all sorts of things: gravity, magnetics, and geophysical logging, and seismic reflection interpretation, just from that one little small job. And this is one of our guys walking with magnetometer across the fields. We didn't have aeromagnetics in those days, so we had to walk across the rice paddies. We also got to do archaeological geophysics there, because this was actually going to be for a coal mine. And there were 2 Buddhist temples in the footprint of this mine that we were going to relocate. And so we did the archaeological geophysics to determine the structures of the foundations, and so that they were going to take this thing brick by brick and relocate it. But sadly, the local opposition to this mine was so strong, because it was going to displace so many people, unfortunately, there was a riot, and just after we left, they burnt the office down, and the mine still hasn't been built to this day, unfortunately. But this is the way it sometimes works out. Another example is when very early in my career, I spent the first 6 months of my career picking seismic records for statics corrections. And then the next 6 months, I worked on T squared, X squared analysis, velocity analysis, and processing seismic data. But that experience, and then further experience I had in government, enabled me eventually late in my career, only a few years ago, to bird dog a 3D seismic survey for carbon geosequestration. So these very early experiences can lead to really, really great, interesting projects. This was 120 farms covered by this survey. Not all of the farmers were on side with the project, but people being people again, and but even though it was a worthwhile objective of sequestering carbon, the people were against it, and they were worried about microseismicity and all sorts of things. But the idea was to actually sequester this carbon dioxide down in a depth. And so this is a map of the area. It's about 60 kilometres by about 100 kilometres. And the interesting thing that came out of this, and this is the surprising thing, that even though it was a 3D seismic survey, the coupling to the ground of the vibrators was directly related to the soil type. And when we correlated the amplitude corrections that had to be made to in the seismic processing to the radiometric, sure enough, the clay soils, or basically, which were very rich in potassium, basically were very good, poor coupling to the ground and absorbing the seismic signal, and the compacted sands over here, which had a low radiometric signal, were actually didn't need much correction of the amplitude. So simple things out of this. So this is just a byproduct of just a 3D seismic survey, that it actually provides useful soil information. You want it when? Well, one of the things you'll find is that that people want it fast, they want it quick, and they want it quality. And when you think about it, in consulting and business, you can only provide two of those. If you want it fast and quick, it won't be cheap. If you want it fast and cheap, it won't be quality. If you want it quality and cheap, it won't be fast. So you've got to be aware of those three things and educate your clients about it. And it's amazing the number of clients that seem to think they can get it all at once. And here's an example of a job we worked on, again, and it's another mine example in Victoria, where the overburden was filled up with what they call fire holes, where in the old days the coal surface was exposed. Lightning would strike the surface. Coal fires would start to smoulder away, even underwater, would you believe, and smoulder away and produce these big depressions in the coal, which would then fill up with soft lacustrine clays and all sorts of things. And then, of course, when you strip the overburden and you strike into one of these fire holes, this is the sort of thing that happens, which disrupted the whole mine for months. So they wanted an answer straight away, but the answer was not that simple, and we had to do about a 2 or 3 year study. And this is the amazing wonder. I always get a thrill every time you collect some data, and it's just a great massive data, and then you put it in the computer. You get this weird Bouguer anomaly, which has got a great big regional effect in it. And then when you take the regional out of using the borehole control, sure enough, you get these beautiful gravity anomalies associated with the fire holes, because the clay is dense and around about 1.9 tons per cubic meter, and the brown coal is around about 1.4. So you get this beautiful correlation. Every time I do this with gravity, the wonder of it just absolutely amazes me. Z. So what's Z? Z is XYZ. Z is topography. The most simple and most elegant and most important geophysical property of the Earth is the elevation of the Earth, because it is the wrinkles and the remnants and the forensic evidence of what's happened to the Earth. In terms of weathering, in terms of distribution and transportation of soils, in terms of reactivation of major faults. We've got plenty of evidence to show that major faults, which may have several kilometres through at depth, they may have occurred under an expansive regime, but when they come back into compression, they reactivate and become reverse faults. And so a few thousand metres of throw at depth manifests as about a 1 or 2 metre amplitude anomaly in the topography. So shuttle terrain model STM data is available over the Earth. So I encourage you, if you're going to do mass area sort of investigations for near surface geophysics, you should look at least at the topography and try and interpret the structures and lineaments from that, and then try and relate it to your other data sets. So both the terrain slope and the terrain itself is very, very important parameter. The other thing is knockbacks. I've got to say, I've been lucky to have I've lost count now, but it's probably well over 300 near surface projects. But the truth be that with a success ratio of 3 or 4 to 1, you pretty well have 3 to 4 times that many proposals that you have to put in to win those 300 projects. And you might think, oh, this is terrible. You know, when you do a research project at a university, of course, you make sure that you're going to have a good chance of getting the funding. But in consulting, it's not that easy, and so you just have to take your chance, be innovative, and put your best foot forward. The more experience you build up, the more methods you've used, the more innovative you can be in terms of your response to the client. You can give them a conforming tender, but you could also give a non-conforming tender. And the number of times that we've won the job with non-conforming tenders because of the experience we've had is very important. But nevertheless, you get these knockbacks, and I think you should treat them as opportunities, because a lot of the innovation and thinking about the work has to go in the proposal stage. You know, you pretty well do about 60% of the methodology framed in your mind when you put the proposal in. So you learn so much from these 3 or 4 times as many projects that you get knockback. So I wouldn't worry too much about those. This is not a knockback project, but it's a project that we use the GEM2 system, which is normally just used in apparent conductivity mode. But if you're very careful about it and calibrate it and do your height corrections and do the drift corrections and so forth, you can actually get very good results. And frequency domain EM works very well if you've got conductive basement and resistive overburden. This industrial site was a greenfield site. There was nothing planned at the moment, but they wanted to know what would be the subsurface groundwater regime if there was industrial spills and so forth. And so we did 3 frequency EM. We used about 10 metre line spacing. The grid here is 100 metres by 100 metres across this site, and leveled the data and corrected it and inverted it. And we came up with a depth to conductive marl, which was the basement, and that was just pretty well sand dunes over the top of that. So you had a good resistive overburden, a very conductive basement. And basically, we were able to just run a simple 2-layer model, and we found that we could predict the accuracy of depths to this interface anywhere between 0 to 25 metres to an accuracy of 1 or 2 metres. It was just incredible. And so we're able to define a subsurface topography of that surface. The surface topography itself, it basically defined sorry, this is the surface topography here. You can see the dark blue dashed lines is really the surface drainage. And then if you look at the subsurface topography of the marl surface in cyan, you can see there's a much different drainage system. So they were able to design their bunding and their plant location and so forth. The plant was able to be basically on the higher ground where the shallower elevation was, and they're bunding, and they knew that if they had any spills, they had to have monitoring bores in these places. Models. We love our models. We just love to have our models, and we're just so engrossed in them. And if you're not in tune with the geology, and you're just a model man, a model person, gaming your data all the time and just fitting it to these very simplistic models that we run, then you can get entranced by your models. But the mantra is that all models are wrong. That some are just more useful than others, and that shouldn't be a reason for not running the models. They generally, each different model tells us something different. I'm fortunate enough to be involved in a project at the moment where we're going to be running 4 different ways of modeling airborne EM data, 1D, 2.5, 3D, and another special way to map the structure. And as well as that, we'll have induced and magnetic 3D models as well. So those models won't be able to, not one particular model will be able to tell us everything about the site, but in certain parts of the site, one model will be more useful than the other. And so if you're a hydrogeologist, and I'm sure most of the people on this call are a hydrogeophysicist, groundwater nerds like me, and I've done probably about 70 or 80 groundwater projects over the years. But the most challenging one is the fractured rock. And how do you characterize fractured rock? It's a very important environment for a lot of arid countries, and particularly for mining sites. And so it's very difficult to sort of fit our crude models to these very, very narrow fractured permeability systems. So one approach we did on one project was to fly airborne EM, and then run an inversion on that. That was a DigEM system that we used, and basically came up with a pretty, I'd have to say, pretty optimistic interpretation of where the fracture systems were based on the block model. You can see that it is very blocky, but is it real or is it not? And then, of course, we went in with ground geophysics and did parallel 2D ERI to try and define some of these bore fields where we thought that might be the case. But in all cases, we found that when you actually go to drill, the results are very, very, still very, very problematical. So if you're looking for challenges in consulting, then fractured rock is certainly one of them. And uncertainty is a great problem for us. I should say later this year, early next year, we're going to be tackling the problem of uncertainty in groundwater, geophysics and hydrogeology. So I'll encourage you to keep your eyes out for that. And that's under this committee that runs these webinars is currently planning for that. This is another one where we've tried to characterize a fractured rock system. I presented this talk at SEG a few years ago. Again, emphasizing this is a team effort. Basically, there's something like about 3,000 disused tailings pits in Australia, for example, many more in the rest of the world. And of course, if you can actually fill them up with tailings and not having to build a new tailings dam, then that would be a great thing. So this client wanted to do that, and they wanted to get permission to do it. And of course, we had to try and show that we could do the best science available, admittedly pretty crude science, but apply our crude 3D resistivity models to this fractured rock environment around the. So we put an electrode in the lake in the bottom, getting it into the water system, and we had 2D resistivity lines all around the pit, and then we ran a quasi 3D model. And on the left, you can see those resistivity lines. It's pretty inadequate, but there was a electrode in the pit as well, and basically we came up with depth slices at different depths. You can see that of course the model is a block model, but this has been contoured into just contours. But you can see that our resolution is not strong enough to or good enough to be able to define individual fractures, but we can we're able to expose different types of rock types, and the contacts between those would probably be the principal concerns in terms of fracture permeability. And this is the part of the problem is with the sensitivity of these models. You can see that there's very high sensitivity around where the lines are and around where the electrode is in the center of the pit there. But as you go further away, the model is less and less reliable. And this reliability falls off pretty rapidly. You know, we're trying to look down hundreds of meters, and you pretty well lose all sensitivity at about 120 meters. So even though we model down to 200 or 300 meters, it's starting to get very problematic down at those depths. So as I say, all these models are wrong, but they do have some use. And the use in this case was really that we just showed that we used the best science available, and that was sufficient to get the permission of the EPA to go ahead and fill that pit, and it's now filled up. It was filled up within a couple of years. The other thing that I'm very strong on is backcasting, because coming back to it being about the geology, and you don't get much more near surface than geology or a geology map, it's also about the application. What exactly is the problem that the client is trying to solve? And of course, we come with it all armed with our models and our wonderful methods and blah, 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 and we approach it, and we'll give you a report with these physical properties, or this seismic velocity or this resistivity or whatever. That they may not want to get those physical properties. They might want to know where the plume is. They may want to know where the weaknesses are of the rock. It might be a tunneling project. It may be a groundwater project. It might be an environmental project. They want to know, where is the best part of the aquifer, or the strongest rock and the weakest rock, and so forth. And so we have to try and transform our parameters into something which is useful and meaningful to the client, whether it's a hydrogeologist or an engineer or just an ordinary environmental scientist or geologists who really think in terms of their we're going back to that picture of the elephant. They're looking at the elephant in a totally different way that we are. So how do we meet these people? And we use this method of backcasting. It's the opposite of forecasting. With forecasting, we look at the weather and we try and predict what's going to happen tomorrow. With backcasting, we put ourselves in the position we're in tomorrow. We've got the result we want. How did we get there? What steps did we take to get to that tomorrow? And that's basically what it's about. The client is up the top here. They have a problem that they want to manage and a site characterization requirement. So we work back from that, and we look at options of what might be able to answer the questions that they need. We do those options, and we agree on what options we'll use going forward. So that implies that there'll be a certain geotechnical model and report. Now the question is, how did we get to that report? What relationships did we have to develop between our parameters and the parameters that the client wants to get there? So we work back to what those relationships will be. Now, how are we going to, then we think, okay, well, we've got these relationships we want to develop. How are we going to actually to work out the calibrations? What boreholes do we have to carry out? What calibration do we need on those boreholes? what are the scale issues, the scaling between the borehole scale and our surface measurement scales, whatever, or our airborne measurement scales, whatever we're using it at. What are those issues? And then we work back to what methods that we're going to be using. And once we know the methods, then we know what equipment and software and expertise we need. And we then know exactly the amount of work and number of traverses we have to do. We work back to that, and we can work back to working out the planning of that project. So it's all result-driven, outcome-driven. It's not, oh, I've got some seismic gear and we've got a guy who's experienced in seismic and resistivity, so we'll just hit the site with that. It's a totally different approach. And whether you're tendering for it or whether you're actually got the job and you're trying to work out how to do the work or to give the answer that the client might want, it's a different approach. Now, there's a lot of uncertainties in all of this. It may well be that we can't develop the relationships, or that there's very great uncertainty about it. But at least we've thought this through from the conclusion back through the methodology. And so empiricism becomes a very, very important thing. You know, you can bypass the models by just, if you've got sufficient geological control and physical measurements, you can correlate those physical measurements with your geophysical measurements. And of course, that's best done in boreholes, where you've got the scale of a measurement is very, very close. The scale of the logging is very close to the petrophysical samples on the core. And so this is an example of sonic interval transit time against uniaxial compressive strength, and it was used for roof strength in a mine. Another example which I worked on at a mine was the plants were dying around a tailings dam because of the saline water that was coming into the system, and so we did an EM survey, and we're able to correlate basically the expected depth of the water table against the EM31 readings. And we also are able to do several years of repeat measurements and show that this tailings dam was a pulsating thing. Depending on the mine throughput and the load on that tailings dam, the water tables were fluctuating up and down. And so we were able to work out error bars around this correlation, and then come up with some sort of risk risk mapping technique for the vegetation, the roots of the vegetation and so forth. So again, in the mining case over here, the engineer wanted roof strength. He didn't want sonic log transit times. He wanted roof strength. And over here, the environmental scientist wanted to know when was the water table going to affect their vegetation. So we could have given them the EM31 readings and left it at that, but we tried to then take it across to the answer that they wanted. But wait, there's more. And I'm going to leave it there because I'm hoping the more will be developed by you when you come and join the great profession of near-surface geophysics. So thank you, and I hope I haven't put you off. I hope I've inspired you to consider a career in near-surface geophysics consulting.
Thank you very much, Jeff. That was a great talk, Jeff, and I hope people find it inspiring. I personally do, despite the fact that I chose a career in academia. You guys have done a lot of really interesting and big work. So that's something that I personally really like. Now, this was targeted for students who want to basically learn how the gears of the industry work with respect to near-surface geophysics. So if you have any questions, please raise your hand, and then we allow you to unmute yourself and ask your questions, or you can use the Q&A box to ask a question if you have any questions from Jeff. So we have a question in the chat that says, I have been trying to get into near-surface geophysics, but the problem is that projects are very sparse and the payment is almost non-existent. How this can be changed?
Well, I guess it's a problem for young people across the board. I think is that this is where your enthusiasm will wear the people down. You know, maybe you have to take a low salary to start with and show that you're enthusiastic. And just don't take no for an answer. I don't take no for an answer. No means I'm too busy at the moment or I can't deal with it. Sorry, go away. Just be, you know, quietly assertive. Don't be rude about it, and just show that you're persistent and you're keen. And I mean, a lot of people. I started as an intern. I basically started as an intern, and then I got a scholarship with the organisation, the Bureau of Mineral Resources, and then they put me through the final year university, and then they gave me a job, and then the rest is, you know, was up to me, basically. It's always up to us. So don't take a victim mentality on this. Just show that you're made of the right stuff. I think that's all I can say. It's unfortunately the way the world operates at the moment.
Yes, I totally can agree with that. And I can attest that you, Jeff, are very persistent, and despite that being in the industry for many years, you never say no to anything, and you still have really great ideas to kind of advocate for the near surface geophysics. We have another question from Desmond asking, I see you did some coal exploration. What's the best technique or method to find coal?
Well, we've used particularly gravity and seismic reflection. It's first of all, it's you can actually gravity. Sometimes the coal beds, particularly if it's if I've worked in both brown coal, which is very, very thick, uncompressed coal, and then later on it gets compressed into very thin bands of black coal. So in the case of that Bangladesh survey, we did a complete a gravity survey of a big graben which contained some of the best coal in the world. We weren't getting gravity effects from the coal itself, but we were getting gravity effects from the structure of the basin, and we're able to define the compartments and the half graben effects and so forth, the transverse faults and all those sorts of things that are associated with sort of rifting systems with the gravity. Then also we were lucky to have some high resolution seismic reflection data, which were able to map the coal directly. As long as it wasn't too thin, it would provide an excellent reflector. And then, of course, when you drill holes, of course, the coal properties stand out quite dramatically on geophysical logs. There are some people that have tried to use electromagnetic methods in the same way. They're probably just as effective as gravity in terms of they're more structural mapping than basically direct mapping of the coal. So you can do it indirectly or you can do it directly.
Sounds good. We have another question in the chat that says, what was the most challenging geophysical method that you encountered in all these years?
Well, would you believe? Right now, I'm working on a multi electrical technique for a dam, and would you believe the SP is the most challenging?
Yes, the signal is very sporadic.
There's so many factors that that you don't have control over. In this case, the reservoir is fluctuating up and down, and I've found to my even at this stage, I'm still learning lessons. I found that there's enormous polarization effects associated with if you're going to do an SP survey, make sure you do it just for SP. Don't put any current through any of the electrodes.
Exactly. Yeah. I'm kind of dealing with that. Have to design my non-polarizable electrodes and everything just for SP.
Yeah, well, that's right. I mean, yeah, that's right. I mean, sometimes we found that an hour and a half after switching off the current, there was still a massive SP effect. Even though we were using alternating current, for some reason, the ground just polarized. Yeah, it's weird. Yeah.
Wow, an hour and a half later. Wow. Another question is from in the chat asking, saying, excellent presentation, thank you. Which software you consider the best to work with near surface geophysics data?
Well, there's plenty of them. One of the things I think we have to be very careful of is the principles underlying the software. For example, everybody's crazy about seismic tomography at the moment, but we are finding more and more as we try to do these this G2HE process, where you try and relate the seismic velocities to strengths and fracture systems and so forth. We find that the RayFract and those sort of seismic tomography programs, they're very good at defining vertical velocity variation, very poor at defining lateral velocity variation. And you have to go back to the original sort of reciprocal methods, generalized reciprocal methods, to pick up the lateral variations. So it's not a matter of which is the best software. There's all sorts of software, preferably a software which has got a good user interface. It's got, particularly if you're in a consulting environment where you haven't got the luxury of being able to learn new pieces of software that you need, you want to make sure that it's as user friendly as possible. But within each sort of category of software, I'm sure there are better ones than others. For example, I like Loki's resistivity inversion stuff, even though he uses a tomographic approach, because he actually tackles the problem of uncertainty, and very few pieces of software actually do that. They give us deterministic answers. So I think the answer to your question, which is the best piece of software, you've got to apply these principles. You've got to apply the principles I've been alluding to. Is it deterministic? Does it cover uncertainty? Is it user friendly? And are there alternative analysis procedures that may give us a different model and a different view of it? I think that's the question you should be using when you're choosing and then of course you've got this brave new world of freeware, which Sina is involved with, of course, and Lindsay and others. And the question, of course, that concerns commercial people is what happens when the person that developed that software is gone, and is it supported and so forth, and can it be developed? So all of those questions, that commercial software versus the freeware. Commercial software is very expensive. Most of the cost of development of software is in the interface. The engines are pretty cheap. It's all that sort of user-friendly interface that it costs a lot of money, and that's why a lot of the freeware stuff doesn't have the great interface, whereas the commercial stuff is expensive and generally has a better interface. But I'm talking in generalities here.
Yes, I totally agree with that. For the freewares, we always advocate for finding new people who are interested in development of software, and it's really difficult to find people who can care that much that the initial developers care about. Anyway, so the next question is that what are the limits of the near surface geophysical methods, or near surface geophysics in general?
Well, they all have their different limits, but as a general rule, as you can see it in that resistivity example around the mining pit, the further you get away from your source and detector, the less resolution you have, whether you're doing it from the surface or whether you're doing it from downhole. The exceptions to this may be things like GPR and seismic reflection. I'd encourage you to spend some time, if you can, as I did early in my career, in the seismic industry, because that is where the best technologies are and where the highest resolution is, and where if you can adapt that across to near surface as much as possible, then we're going to get better and better techniques in near surface. But a lot of the potential field methods are very, very, very poor in their resolution, very general in their interpretation, and ambiguous in their interpretation as well, whether it's magnetics or gravity. Even some of the EM methods, for example, EM methods are really very good with detecting conductive terrains, and but not so good with resistive terrains. Resistive methods are good for resistive terrains, but there's some uncertainties with conductive beds because you can't get the current beyond those and so forth. So it's again, it's a very general question that you've asked, but you'd have to look at each method on its basis, and it's only by, as I say, only by spending 1 year at least concentrating on one method that you would start to learn what its limitations are.
Right. Thanks. Another question is that which is the best technique to define phreatic level in soils?
The phreatic level, was it?
Yes. Yeah. What technique is better to define that?
Well, I've tried using radar. I've tried using EM, and I've tried using the towed resistivity systems like OMAPA. It can be complicated by the salinity of the water. It can be complicated by the clay content of the soil. And yeah, I think again, you just have to try. I mean, I think as a general rule, radar is good at picking up, as long as it's not stopped by near surface clays. It's generally pretty good at picking the water table directly and probably most accurately. I'd say radar is probably your best technique in terms of trying to map that surface. But again, if it's a vadose and it's a sort of a continuous, it's not a clear water table, that can be problematic as well.
Thanks. There is a comment there from Bill Newman saying that if you're looking for a career in practical career, basically private industry and private sector is not just the only place that you can go. There's numerous agencies, government and non-government, that can employ near surface geophysicists, and many are offering internship. I know for the fact that USGS is actively looking for interns in the US, so that's one of the places that if you want to look for internships, there are many places that you can look for that aside from the private sector. Another question is that asking that, again, not a question, says in Africa, equipment and software are the limitations for us. There is another question that I think was answered. What are the challenges involved in interpreting subsurface structures and properties from the geophysical data? I think we answered that kind of in the context of your presentation. The next question is asking me to look at my email. Another one is that how do near surface geophysicists integrate geophysical data with other type of information such as geological mapping, borehole data, and satellite imagery?
Yeah, well, I think again, one of the things that I did, one of the most important things I did was took a course in remote sensing, and using the remote sensing software tools, we can relate our magnetics grids, our radiometrics grids, our topography grids, LiDAR, etc., to geochemistry, to spectral reflection, hyperspectral, satellite Landsat, right down to the high resolution satellite spectral responses. We can use the classification algorithms that they have developed for Landsat and satellite processing. We can just consider them as another band, our methods as another band, and do that. So you can actually integrate spectral reflectance with magnetic response, or with radiometric sort of in the potassium, uranium, thorium, and so forth. That's a good best method that I know of integrating those. I did give a talk here in Portland at the GSA conference on that very subject of how you integrate and use all of these data sets for geological mapping, because we now have, we're very lucky if you go to a site and you've got 100,000 scale mapping, but most of our geophysics is mapped at probably 25,000 or 5,000 scale. And so there's a lot of geological information tied up in that if you can actually integrate it and interpret it,
Agreed. Another question is that, again, what is the best method to interpret the subsurface? I think that is a very general question, and you kind of answered that about a couple of questions above. Another question is, what are the strengths of near-surface geophysics? Because I think you answered the limitations. So what are the strengths of the near-surface? How do we advocate for this to people who don't know anything about near-surface geophysics?
Well, I think it's about the scale. Boreholes give you a very, very precise information. Admittedly, a lot of the time the borehole properties, if they haven't been cored, can be quite disturbed. So the strengths of it are, firstly, if you log the hole geophysically, you actually expand the information you get from the drill cuttings and from the core itself. But you do it at that sort of borehole scale, and then between boreholes is a big gap. And this is where our surface geophysics, our airborne geophysics, our borehole to borehole tomography geophysics can fill those gaps. And you'll get very precise information at the boreholes, very general information at a different scale between the boreholes. And there's a bit of an art and a bit of a science in relating those two different scales and taking that into account. But the point is, I can show plenty of examples where boreholes have just been drilled, on a gasology basis, a hydrogasology basis, or a geological guessing type basis, or they just drill at regular intervals along a pipeline or on a grid and so forth, with no understanding of what the site characterization is. If you drill one borehole, your model is a horizontal layered geology, which is the geological log of the borehole. You drill two boreholes, you might have a slightly more complex geology. If you have three boreholes, it's even more complex. But there's a big gap in between all these boreholes, and so the geophysics fills those gaps, but it has to be applied intelligently.
Awesome. One last question that I think it's a very good question is asking that for those of us who are doing oil and gas geophysics work, such as seismic interpretation, and trying to transition to near-surface geophysics and change career, what are your recommendations for a smooth change? As there would be a lot of knowledge that people don't know about near-surface, lack of experience in a lot of near-surface methods, but they have a lot of experience in seismic, specifically for exploration.
Yeah, well, the obviously transition path is through seismic reflection, scaling it down, high resolution seismic reflection. The other thing is that people in the oil and gas industry are generally switched on to petrophysical stuff and logging. But the other methods, I think you just basically have to, we're always learning, right? We're always learning new methods, new techniques. You're just going to have to slowly learn and accept the fact that the resolution of your techniques other than seismic and geophysical logging is going to drop off enormously. And you're going to have to work with that. And it's a cultural shift in your thinking, and it's a cultural shift in how you use this information, how you deal with the uncertainties that arise because of the poor resolution or so forth. But be conscious of scale, be conscious of again, I mean, knowledge just changes. I mean, they say that our knowledge doubles every 10 years, right? Now, I've been out of university for 50 years, so 2 to the power, the knowledge has increased 2 to the power 5 in that time, if you believe that mantra. And in the time that I've been out of university, it's the same thing when you transfer from one discipline to another. You've got to learn a whole bunch of new skills, and there's no getting around it. You just have to do it. And again, this is where your enthusiasm, your ability to adapt and bring what skills you have, but show that you're keen to learn new skills. That's all I can say, really.
Thank you very much, Jeff. There are some standing questions in the chat and Q&A. I'm sorry that we can't answer all of them right now. Please ask these on our Slack group, and a person who's doing that will reach out to you and answer. That's our hope with having this Slack group. Or you can directly reach out to Jeff if you have any specific questions regarding his presentation or his experience. Thank you very much, everybody. Thank you specifically, Jeff, for spending the time and having this great presentation for us. See you at the next webinar.
Yeah, thank you. Thank you, Zena. Thank you, everybody.